So as I was telling about this pretectic and the type 3 diagrams and type 4 diagrams, right? We looked at different types of diagrams. Like type 4 I haven't yet gone. So I am looking at type 3, but you need to understand that from type 2 we can basically go to type 3 in this way, that you have ideality. So when you are looking at these lens diagrams, for example, you have liquid, and then you have this lens like region where you have liquid plus solid solution, alpha solid solution. So this is like liquid plus alpha solid solution, and this is also a solid solution, right? So basically alpha is your solid, basically alpha is your solid. Now this here, the liquid, in the liquid it is infinitely miscible, right? A and B are infinitely soluble. In the alpha also, in the solid solution also, A and B are infinitely soluble, right? They are completely soluble. So in this case, you can basically use an ideal solution concept for describing liquid and alpha. So liquid can be described as an ideal solution, alpha can be described as an ideal solution, right? And basically in such a case, what you will have, you have this lens shift, two-phase region, right? This is this lens shift two-phase regions, like it looks like a lens where, and this is pure A, this is the pure A melting point, this is pure B melting point. Now, however, when you want to go into this type 3 type of phase diagrams, type 3 phase diagrams like eutectic and pretectic phase diagrams, then you require to introduce non-ideality. Now, when I talked about ideal solution, what did we tell? We told that the enthalpy of mixing is equal to 0. So, if we look at non-ideality, or if we want to introduce non-ideality, we have to change the enthalpy of mixing, and the enthalpy of mixing in the liquid and the solid will not be equal, right? So basically, if I think of this, that in the solid phase the enthalpy of mixing is more than in the liquid phase, and in both cases the enthalpy of mixing is positive, right? Enthalpy of mixing is, so basically what I am looking at is, we are taking enthalpy of mixing is positive in both liquid and solid solutions, right? So enthalpy of mixing is positive in both liquid and solid solutions. So that's what I am talking about. So, right, so basically if the enthalpy of mixing is positive in both liquid and solid solutions, and if enthalpy of mixing, so please look at this condition. So have a look at this condition. Delta HM alpha, which is greater than 0. Delta HM liquid is also greater than 0. In addition, they are unequal. That means delta HM alpha is greater than delta HM liquid. So basically, in other words, what are we looking at is basically this, that in the, so basically from lens is type 2, right? Lens is type 2. From type 2, if I have to go to type 3 phase diagram, then first of all, delta HM, in type 2 you have delta HM, that is enthalpy of mixing, molar enthalpy of mixing for the, right? So delta HM mix for the alpha phase, say for example, for alpha is 0, and delta HM mix. So this is for the ideal lens like conditions, right? This is for type 2. So this is for type 2. But for type 3, what you are telling basically, so this is type 2, or where you have, so this is where you have complete solubility in liquid and solid solutions, and in such case you get type 2 phase diagram. And also one of the things that it has a shape, a lens. These phase diagrams are typically lens shaped, where you have a lens shaped region, lens shaped two phase region. Now, if you make delta HM mix for alpha greater than 0, as well as delta HM mix for liquid greater than 0. In addition, you are also telling that delta HM mix alpha is greater than delta. So basically the enthalpy of mixing, delta HM means molar enthalpy of mixing for the liquid solution. So molar enthalpy of mixing of the solid solution is greater than the molar enthalpy of mixing of the liquid solution, right? The molar enthalpy of mixing the liquid solution is less than the molar enthalpy of mixing the solid solution of A and B, right? And both are positive. That means delta HM mix alpha is greater than 0. That is enthalpy of mixing, molar enthalpy of mixing the alpha phase is greater than 0, in the liquid phase is greater than 0, and that in the alpha phase is greater than that of the liquid phase, and both are greater than 0. In such case, what you get is deviation from ideality, or you get non-ideal. So this is like increasing delta HM mix means this is also non-ideal. So today, if I tell that this is non-ideal, this is not, that is wrong, right? This is also non-ideal. This is increasingly non-ideal, and this is also non-ideal. So we can tell in this direction increasing delta HM mix and also increasing non-ideal. So increasing deviation from ideality is basically towards the from left to right. So here you have ideal lane shift. Now you see in a non-ideal system at a lower temperature. Remember, this is temperature axis, right? This is temperature axis. So at a lower temperature, you basically have this alpha phase which can now phase separate into alpha 1 plus alpha 2. So alpha can phase separate into alpha 1 plus alpha 2, right? At a temperature that is below a critical temperature. So say there is a critical temperature TCR. Below the TCR, you have alpha 1 plus alpha 2 coexistence, and here you have alpha 1, here you have alpha 2. Now, with increasing, means it make it more positive, make delta HM alpha more positive. If I make delta HM alpha, there is a molar enthalpy of mixing. So this is delta HM mix. Remember, this is delta HM mix, and this is also delta HM mix. So delta HM mix alpha or delta HM mix liquid, if we make them more positive, or particularly if we make, so in this case alpha goes to alpha 1 plus alpha 2. So if we can make the molar free energy of mixing more positive, then basically what we are trying to say is that the critical temperature, so basically the critical temperature is such that, or the phase diagram change is such that the miscibility gap, so the miscibility gap region meets the lens like region, right? Means this two phase coexistence region of liquid and alpha, or liquid and alpha 1 and liquid and alpha. It can be liquid alpha 1 or liquid plus alpha 2. Now it is basically meeting here. Now you can see that this is meeting here. The miscibility gap meets here. Now if it goes further, so you may increase it further, what you will see is that miscibility gap now enters the lens. It is entering the lens, and then the lens converts into a region like this. The lens converts into a region like this, right? This is the region that where the lens converts, and this one, basically if you see these one, and you see the miscibility gap has entered, right? So this is that purple colored line is the metastable portion, right? It's the metastable portion of miscibility gap, right? This is with increasing delta HM mix, that is increasing molar enthalpy of mixing and molar enthalpy of, remember two things. One is increasing molar enthalpy of mixing, and molar enthalpy of mixing has to be positive. If you, as you have shown in regular solution, that if molar enthalpy of mixing is sufficiently positive, then only you get something called a miscibility gap, right? We have already shown that. So basically remember this point, okay, that we have discussed previously. Now if you see, you have this alpha 1 plus alpha 2 here, but you see now this guy has gone inside the lens, and the lens has now converted into a two-phase region, L plus alpha 1. So you have L plus alpha 1, and then you have alpha 1, and alpha 1 plus alpha 2, L plus alpha 2 and alpha 2. And again, this is like a peritectic point. But please remember that there is this metastable submerged miscibility gap, right? This miscibility gap has entered the lens and it has converted with increasing non-ideality or increasing positive enthalpy of mixing of the solid solution. You basically have entered into a regime where the miscibility gap has become metastable, and what you have got is a peritectic phase diagram or a peritectic reaction, right? At this point, if you look at this point, say for example, call this P, so this is a peritectic reaction. Now, okay, so type 3 you have looked at peritectic phase diagram. Just previously we looked at peritectic phase diagram, but we also looked at eutectic phase diagram. Is it also possible for eutectic phase diagram? Indeed, it is, because again, you see, you start with ideal, you increase the enthalpy of mixing and it is positive. So you can see that the enthalpy of mixing of the alpha phase, that is the solid phase, is more positive than for the liquid phase, and as a result you have this miscibility gap, right? And not only this miscibility gap, now this lens has broken into two pieces. If you see that, it has not really broken. This red line is continuous, so this is basically a continuous, but it has now changed its curvature, right? Near a composition, it has changed its curvature. So it looks like a double lens, right? You have one lens here, and you have one lens here, and you have one region, a very small region, where there is a change in curvature, a rapid change in curvature that is happening, and then this is the liquidus. So the liquidus has changed this way, right? It looks like two L plus alpha regions separated by one L region, right here, and then that is in equilibrium with alpha, and below a certain temperature, again below the critical temperature, again alpha converts to alpha 1 plus alpha 2, right? That's the transformation inside the miscibility gap. Now think of this, you make it more positive, you make delta HM mix alpha more positive, then basically this miscibility gap grows, right? It grows. So that's what I am talking about. See, for example, it has grown here, right? It has grown here. So if you see here, it has grown. So it has grown and it has touched this point. Now once it has touched this point, you see basically there is a coexistence of liquid alpha 1 and alpha 2. There is no alpha anymore. You see, once the point has been touched, you have alpha 1, alpha 2 and liquid. You do not have alpha anymore, right? Previously you had an alpha solid solution, again below a critical temperature. This alpha transformed to alpha 1 plus alpha 2. Now, as you make it more and more positive, delta HM mix alpha more and more positive, delta HM mix liquid more and more positive, particularly this guy. So if you make it more and more positive, you will see that the miscibility gap now touches exactly one point, and at that point, liquid alpha 1 and alpha 2 coexist, right? Now, see, you cannot have more than 3-phase coexistence, right, in a binary solution, right, according to Gibbs phase rule, because if you have more than 3-phase coexistence, then basically your degree of freedom goes to -1, right? You should have a maximum phase coexistence that you can have in a binary solution is 3 phases, right? So exactly like we have read this invariant reactions like the peritectic reaction or the eutectic reaction. Now you can see that if the miscibility gap progresses further with increase in delta HM, okay, increasing the molar enthalpy of mixing of the alpha phase, if your miscibility gap enters, now the miscibility gap enters or advances further, right? It advances further. So at higher temperatures also there is a miscibility gap. Basically, you have a miscibility gap now at a higher temperature. Your T critical is increasing. Now your T critical has increased somewhere here, say. So basically your miscibility gap will now go like this, right? And exactly that's what I've drawn. Now you see this miscibility gap, this portion of the miscibility gap now becomes metastable, right? This becomes metastable. If liquid phase is absent, then you can basically think of this miscibility gap, right? The submerged miscibility gap. Otherwise, it's a simple eutectic reaction where you have L here, you have L plus alpha 1 here, L plus alpha 2 here, and this is the eutectic point, and at the eutectic composition and temperature, L transforms to alpha 1 plus alpha 2. It's a mixture of two phases, alpha 1 and alpha 2, right? This is how a phase diagram evolves as a function of non-ideality, and where the non-ideality is introduced by making the enthalpy of mixing positive for both the solid and the liquid phases, and also making them unequal such that the enthalpy of mixing of the solid phase is more than that in the liquid phase, Okay, and we are considering a binary ABLR. So you can see the evolution of phase diagram or phase stability map, right? So once you have done that, now we'll quickly go through the type 4 and type 5 phase diagrams. Type 4 phase diagrams is basically you have an unstable stoichiometric or non-stoichiometric compound. Unstable means unstable. So stoichiometric compound. What does stoichiometric compound means? It has a very fixed and well-defined composition. For example, AB. AB contains 50 atomic percent A, 50 atomic percent B. Right? AB cannot be obtained, or AB, if you have a fixed composition AB, there is no other combination of A and B, 50 atomic percent, 50 atomic percent, other than 50-50. You have no other atomic composition that will produce this AB compound. Similarly, A to B, you have 1/3. So you have 1/3 B and 2/3 A. So basically, 2/3 of the atoms will be of A, and 1/3 of the atoms will be of B, and that basically will be exactly 2/3 is to 1/3. So that is 2:1, and this A to B formula does not change. Or AB3. AB3 means you have 1/4 A and 3/4 B. So these are stoichiometric well-defined compositions. However, there are also non-stoichiometric intermediate compounds that can form, which has a new crystalline arrangement other than the terminal solid solutions. They have new crystalline arrangements. So think of the eutectic diagram. Inside, if you insert a phase boundary within the eutectic diagram in the two-phase region, that's an intermediate phase. But the intermediate phase should have a different new crystalline arrangement, but it will also have variable composition. Now, if you are non-stoichiometric means the compound has variable composition. Say, for example, A. So this is a compound, a non-stoichiometric compound, where A can vary between 55 and 60, and B can vary between 45 and 40. Right? A can vary between 55 and 60, and B can vary between 45 and 40 atomic percent. Right? So in A is 55 atomic percent, say for example, B is 45 atomic percent. If A is 60 atomic percent, B is like 40 atomic percent. So A can vary between 55 and 60. So basically, you have some solubility in this non-stoichiometric compound, right, of B. So you have a varying solubility of B in this non-stoichiometric phase, right? So in stoichiometric, it's like a line compound, and here it is again a phase region, right? This is a phase region, and here it is like a line compound. So this is a line compound. So let me write here, and here it is again area, right? So this is a line compound, and here it is like area or region, right? You can call it. It's a new single phase field. Now this single phase field has a composition which varies, where A varies between 55 and 60 atomic percent, while B varies between 45 and 40 atomic percent. So this is one example where it is unstable. See, basically, if you look at this, there is a eutectic here, right? If you look at this, there is a eutectic here, and there is a peritectic here, and you have this intermediate gamma phase, right? If you look at this, you have this intermediate gamma phase, you have liquid plus alpha. So immediately, whenever you mark a phase diagram, you first look at or identify the single phase regions. For example, this is a single phase region with degree of freedom 2, and we mark it as alpha. Single phase region with degree of freedom 2, mark it as beta. Single phase region with degree of freedom 2, mark it as L. Now, why L here? Why not L here? Why L here, not here? This is because liquid will generally form at a temperature higher than the solid, right? Because solid requires heat to convert to liquid, right? So liquid will always be at stable at higher temperatures. Now you see, you also have now another single phase field called gamma. Now this gamma is basically appearing somewhere in between alpha and beta. Now if you see this gamma, there is one interesting point that I want to tell you, that above Tp, gamma is gone, right? Gamma has converted to L plus alpha. And below Te, gamma has converted to alpha plus beta. So this is an unstable compound, and so unstable because it is not stable at all temperatures. It is not stable. So it is basically, what does unstable mean? Unstable means so these are unstable, right? Presence of an unstable, right, compound. So unstable means that it has upper temperature limit for stability as well as a lower temperature limit, right? So basically, if I go below T, it does not remain as gamma, but it changes to alpha plus beta. Alpha plus beta are the terminal solutions, right? Gamma changes to alpha plus beta. By the way, this transformation is gamma to alpha plus beta is called eutectoid transformation, right? It is very similar to eutectic transformation. So you have this gamma phase and you have again this particular temperature TE, okay, at which you can see here you have gamma phase, you have alpha phase, and you have beta phase. So you have degree of freedom equal to 0. And basically, what I am telling is the gamma phase has a different crystal structure than either alpha or beta, right? That is the point. So, but gamma phase is an intermediate phase, but it's also having a limited solubility, because if you are within TP and TE, it exists, but above TP it does not exist, or below TE it does not exist. So, we come to another phase diagram which is called presence of stable. So, stable means it will not be stable at high temperatures, but it has to be stable at one temperature. For example, if I look at this line compound A2B, okay, so I look at a stoichiometric case and I look at a non-stoichiometric case. So if I look at the line compound A2B, so basically you have L and you have pure A, so L plus A and then A plus A2B, A2B plus B, and this is the line of A2B. This is the line of A2B. Now, as you can see, A2B basically solid. This A2B solid, when it changes to liquid, basically the composition of A2B has been disturbed, because now the composition, as soon as it enters here, then it has this composition, right? This and the pure B composition. Now again you go, so instead of going there, you go here. Again you have this two-phase composition, right? Your liquid phase composition is changing. So that means it is an incongruently melting compound. A2B is an incongruently melting compound, because when it melts, the composition in the solid state and the composition in the liquid state are not all the same, right? The liquid composition has changed from A2B, right? A2B was the solid line compound composition, but as soon as it changes to liquid, the liquid composition has changed, right? So this is a line compound, right? This is what I am calling a line compound, because it is a line, right? It is exactly stoichiometric A2B. However, you may have an A2B as a central structure. You can look at the blue line here, a blue faint line I have drawn. But if you look at this, this is based on A2B. This gamma structure is based on A2B, but gamma has now some solubility. How? And some limited solubility. How? See, A2B is in the middle, but it can be slightly different from A2B, right? So at this point, you can have difference than A2B. And so if it is slightly different, so what does this mean? This means that gamma, although is a non-stoichiometric compound based on A2B, in gamma, the composition of A can change and composition of B can change within a limit or within a range. That is the point. So if at any given temperature, for example, if I look at the gamma phase field, okay, you cannot draw any tie line here. Remember, you cannot draw, it's a single phase field. Now, if you look at gamma region exactly behaves like a A2B, right? Only thing, it's a region, while A2B is a line compound. A2B is a line compound, but gamma is an intermediate region. And remember, as you go down the temperature, gamma is quite stable. Similar is for A2B. However, when gamma melts, or if gamma, say for example, the gamma goes here and wants to go into the two-phase region of liquid plus alpha, what will happen? You will have gamma, and then gamma should go to liquid plus alpha. So what will basically happen is the gamma will melt at a different compositions, right? It will not melt at the original composition that it have. So it will have a different alpha solution consistency. So basically the composition of alpha solution will vary, right? Because it is given by the tie line. For example, if I just look at these tie lines here, so this tie line or say this tie line. So we have drawn just two. Okay, so basically I have drawn just two. So one. So as you can see, with gamma, when it melts, basically continuously changes the composition of the liquid, the composition of the alpha phase. So basically the gamma, whatever composition it started with, it can be like A55. So it is based on the A2B structure. That's what I can say. The gamma is based on A2B structure. However, it has some limited solubility of A and B, right? So basically, if I look at this temperature, if I look at some temperature, say for example, let us look at a temperature like this. If you look at this temperature, first thing first. See, you can only draw tie lines here. So now if you look at this, the gamma composition basically that is in equilibrium with alpha is given by, so this is some temperature, say for example, let us call this temperature say T1. Now at T1, you have gamma beta equilibrium as well as alpha gamma equilibrium. So you basically know the phase boundary compositions. You know the phase boundary compositions. So basically, you are looking at the phase boundary compositions here, right? And so you have basically gamma in equilibrium with alpha, gamma in equilibrium with beta. But as you go above, right, as you go up the temperatures, right, as you go above, then basically, if you go like this, then basically the liquid phase that forms will have a different composition than gamma phase, right? It will have, so any composition, I can take some composition here, even if I take some composition here, as you go here, say for example at this temperature, you basically have now a liquid composition which is different. You go to this temperature, you have a liquid composition which is different. You do not, so basically, what does that mean? It means that again, this is an incongruently melting solid. Now, let us look at a congruently melting solid case, where again we are looking at two compounds, two line compounds. One is called AB, another is called AB is like 50A, 50B, another is A2B. So now, if you look at that, A2B extends from some room temperature or nearby room temperature. It goes on and on and on and on until it hits the liquid. So basically, A2B, when it converts to liquid, A2B itself, when it converts to liquid, the composition of A2B does not change. Liquid also has the same composition A2B, and these are called congruently melting compounds. Okay, these are called congruently melting compounds. In fact, you also have a incongruently melting. See, you have an eutectic compound here. You have an eutectic here, right? You have because you see the diagram here. So you have an eutectic here. You have again so basically you have a peritectic here, and again you have some eutectic. L plus AB, L plus B is AB plus B. But the point that I want to make here is that this compound AB is incongruently melting solid, right? It's an incongruently melting. As soon as you enter here, basically, what you are basically seeing is the composition, right? And now again you go here. Now you see there is a change in composition. So basically, we have to remember what is, so basically AB is incongruently melting while A2B is congruently melting. Now again, we can think of some solubility, and we can think of like it is not exactly line compound but a phase bound. So basically, if you look at this gamma phase, it has a different structure from alpha and beta, and this gamma phase basically is based on this A2B composition, but A is now allowed to vary within some limits, and B is now allowed to vary within some limits as a result. So as a result, what you see is this gamma phase forms. But now, if you go to this A2B composition within the gamma phase and again extend the horizontal line, you will basically see that you have ended up with the melting of this composition. Say, for example, if I take this guy, out, so let us look at these. Okay, so let me just think. Just do that. Now, let us have So this is called a congruently melting solid. So basically, for this congruently melting solid, which lies in the gamma region, basically converts to L, right? Basically converts to L. That's all, right? So you basically have now type 4 phase, type 5 phase diagram. Again, here as you can see, type 5 means intermediate phases that are stable and extend extend on either side. It can extend on the liquid side or it can extend towards the room temperature side. But only thing is the previous one, type 3, was having this problem. Type 4 was having this problem, that it is stable within a temperature range. However, if you look at this carefully, where I have drawn, so basically what you see is that it is a congruently melting solid, okay, for the given or specified composition. So that given or specified composition here is based on A to B. So this is basically, right, this is nothing but right, this is the A to B composition. Now you have type 6 phase diagram, which is basically a very important phase diagram. We have already introduced that. This is called miscibility gap, and this happens when you use a regular solution model or some non-ideal model. In a non-ideal model, you are basically telling that there is a finite delta H mixing in the liquid state or in the as well as in the solid state. So you see this is a liquid miscibility gap or liquid miscibility gap where you have one liquid, which is phase separating into L1 plus L, right? So this is called a liquid miscibility gap. So you see liquid miscibility gap, as well as if you look at this diagram, you see alpha basically is a solid solution. Now if you see there is a TC or a critical temperature TC, right, at below which the alpha phase separates spontaneously into alpha 1 and alpha 2. It phase separates. Basically, we can tell it phase separates alpha 1 and alpha 2. In the miscibility gap, then again there is a catch to basically distinguish between whether the phase separation is spontaneous or it is non-spontaneous, right? So basically, what I am trying to say here, I am not looking at phase transformation, but I am looking at phase diagram. So this diagram basically tells you that if you have a homogeneous solid phase alpha, and there is a critical temperature below which the alpha can phase separate into alpha 1 and alpha 2. Only thing that you have to remember is that alpha 1 and alpha 2, alpha 1 and alpha 2, in this case, when you have a miscibility gap, you assume them to be structurally same. Basically, alpha 1, if alpha is FCC, alpha 1, so it's like silver copper mixture. So if you think of a silver copper alloy, silver is FCC, copper is FCC, so alpha is FCC. But now when alpha decomposes into alpha 1 and alpha 2, which one is like Ag rich solution or silver rich solution, and another is copper rich solution, you will basically see that alpha 1 and alpha 2 also possesses the same crystal structure, as the parent alpha phase. Okay, so and also again, if you look at some temperature T2, just for convenience, if you look at some temperature T2, you can see that. So this, if I have to mark this is basically pure alpha 1, this is pure alpha 2. So basically, if I have to mark this, so this is the composition, or this is the composition of coexistence of alpha 1 and alpha 2. So there is this equilibrium, right? So the equilibrium coexistence between alpha and alpha 2 occurs at this composition and this composition, right? X equal E alpha 1 and X E alpha 2, right? At these compositions, at this temperature T2. Okay. Now, as you can see here, it is clear now that this miscibility gap, now if you have a eutectic phase diagram, there is always a submerged stable miscibility gap. If you can basically somehow suppress the formation of liquid, then you will have basically, so you will have alpha, which is metastable, and this alpha changes to alpha 1 plus alpha 2. Currently, what you see is not a metastable microstructure, but if you follow this exactly the yellow lines, basically L2 alpha 1 plus alpha 2 will still happen. However, the mode of decomposition will be different, right? L2 alpha 1 plus alpha 2. The mode of phase separation will be different. However, you please note that this submerged miscibility gap helps us understand why some phase separation happens in such during such transformation, during transformations like eutectic transformation, peritectic transformation, and so on. Okay, even spinodal, right? So this miscibility gap, this submerged miscibility gap or metastable miscibility gap that we find when we reject L, right? When we reject L or when we suppress L and or liquid, and we basically tell that it is alpha, alpha 1 and alpha 2 are the phases, right? Alpha is the phase above a critical temperature. Again, remember the concept of critical temperature. This is very important. So this is our critical temperature, say. Now at this critical temperature, the alpha phase as well as the alpha 1 phase and the alpha 2 phase can coexist. Again, we are suppressing L. So alpha is the metastable parent phase, and alpha 1 plus alpha 2 is still not metastable, but basically alpha 1 plus alpha 2 are basically the stable phase separated phases, right? Which are isostructure but not isocompositional. They are different compositionally, but they are similar structure, correct? So you have the submerged metastable miscibility gap, right? You note that this is a submerged metastable miscibility gap. So metastable means if the formation of liquid is suppressed and you form this alpha solid solution, which is a metastable solid solution at this temperature, then below this critical temperature, it will phase separate, right? So we are done. Now we look at, very quickly, we look at the free energy composition diagram. We start with the free energy composition diagram. And remember, this free energy composition diagram, from there, you can explain the phase diagram or phase stability maps. Why? Because free energy composition diagram tells you in some way. See, for example, already we know from free energy composition diagram that at any point you can draw a tangent and you have this tangent intercept method, and the intercepts basically give you the chemical potentials of the species, right? Species A and species B, right? We know that. Also, another thing we know that for ideal delta GM mix, ideal will only contain the entropy term, right? And it will be parabolic, right? Now, if it is non-ideal, AI is not equal to xi. But if it is ideal, then AI equals to gamma xi. Now, if you see gamma is greater than 1, this is type 2. So, type 1, when I have this 1, the free energy 1, here basically we are telling that delta H mix is 0. Delta H mix or molar enthalpy of mixing is 0. So, basically 1 is the ideal. It is the free energy of the ideal solution. 1 corresponds to the free energy of the ideal solution. 2 corresponds to the free energy of a solution which deviates from ideality, but the deviation is positive. That is gamma I, which is the activation coefficient, in 2 is greater than 1. In type 2 phase diagram, in the type 2 free energy diagram, that's basically this. When I mark 2, this is 2, and this 2 corresponds to this free energy, this green free energy. The green free energy shows positive deviation from the ideal case, and this positive deviation means gamma I is greater than 1 and AI is greater than xi, right? Now, if you look at curve 3, the curve 3 basically represents a negative deviation from ideality. Ideality is given by Raoult's law, AI equal to xi, but in general, where gamma equal to 1, but AI equals to gamma xi. So if you see the type 3, the third, okay, the marked as 3, not type, you call it level. So the free energy corresponds to level 3. The free energy corresponds to level 3. If you look at that, you will see that at any point here in type 3, gamma is less than 1, right? You are basically falling below 1, right? You are falling below 1. So as a result, if you are below 1, that means there is a negative deviation from ideality. So this gives you a negative deviation, and this gives you a positive deviation from ideality. This gives you a negative deviation from ideality, right? And negative deviation means gamma is less than 1. Positive deviation means gamma is greater than 1. Ideal, there is no deviation means gamma equal to 1, right? So that's right. Now, if you see, you have BB, BA, and BC. So you can basically write BB is nothing but the intercept delta GB bar, or right, BB is also delta GB bar, BA is also delta GB bar, and BC is also delta GB bar. But this is delta GB bar for BB is delta GB bar for type 2. Now, if you see RT, ln AB, so delta GB bar is the partial molar free energy of mixing associated with the beta, associated with B. Like partial molar free energy of mixing associated with B. So delta GB bar is RT ln AB2, right? So this is basically AB corresponding to 2, right? 2 means where gamma I is greater than 1. Gamma I is greater than 1, or gamma B you can write is greater than. Now in this case, for the case R, BA is the intercept, right? This BA, what is this BA intercept? This intercept basically gives you mu B, right? For the ideal solution, right? This is basically delta GB bar equals to mu B. Okay, and this mu B is for the ideal solution, right? We are doing it for some ideal solution. So then this is the ideal solution. So here activity is equal to mole fraction. These are non-ideal. So here remember this is basically BC and this is basically BB, and you can immediately see that BB, that is the intercept BB, is larger than BC, right? So it has a negative deviation from ideality, right? So Raoult's law, if you write AB versus XB, so this is again a recollection of the previous lecture. If you see that you have this 45-degree line and that where AB equal to XB. Now the deviation can be positive and the deviation can be negative, right? But Raoult's law tells basically it's a straight line, right? And as soon as there is deviation, that means gamma is not equal to 1, you will start seeing either a positive deviation or negative deviation. So 3 gives you negative deviation from ideal condition and 2 gives you negative deviation from positive deviation from ideal condition. Right, now we come to a very important concept called free energy, the equilibrium, chemical equilibrium, and we know chemical equilibrium very easily. So if we look at this, you have these two free energies, right? We can say at temperature T1, I am drawing the free energy curves for 2 phases, right? There is a liquid solid coexistence, right? If you have a liquid solid coexistence, then basically at temperature T1, we are drawing, say for example, the free energy composition curve. Now, if you are looking at the free energy composition curve at temperature T1, right? Temperature T1 is fixed, right? You have the liquid curve. This is the liquid free energy. Okay, we are assuming again this is ideal solution. So liquid has some parabolic shape, right? Liquid free energy and the solid free energy, right? It is RT, XL and XA plus XB and XP, right? So liquid and solid. If you look at liquid and solid. This is the liquid and this is the solid. So this is your solid free energy and this is your liquid free energy. Now if you see, for any given composition, I can draw a tangent. Now if I draw a tangent to the liquid phase, what will you get? I'll get on the left hand side we'll basically get for the liquid phase we will get mu A liquid, right? We'll get mu A liquid, right? And you will also get mu B liquid. Are you seeing that? So you have mu A. This is basically the diagram. So you have mu A liquid and you have mu B liquid. Similarly, if I look at the solid free energy curve, the solid free energy curve, then we are looking at, right? This is the solid free energy curve. And basically, again, we are drawing some tangent, some arbitrary tangent. Again, the intercepts basically gives me. So, don't be confused. So, I'll do one thing. I'll just write it with a different color. So, basically, mu A solid, right? And this is mu B solid. Okay. Now, if you see, if I want to have a liquid solid equilibrium, like two-phase coexistence means they are at equilibrium. Right? Two-phase coexistence means they are at equilibrium. Liquid and solid are at equilibrium. Now, if I want to see the equilibrium graphically, how do I do that? Because you have two tangents. Now, you have to remember that you have mu A solid, you have mu A liquid, you have mu B solid and mu B liquid. How do you basically find the equilibrium? So, you remember at equilibrium means here I am talking about chemical equilibrium, chemical potential of each species. So basically at chemical equilibrium condition, is mu A solid equals to mu A liquid. Another is mu B solid equals to mu B liquid. Right? That is the chemical equilibrium, the well-known chemical equilibrium condition. Right? So now if you look at that, if you look at this, then there is an interesting point around that. So basically mu A solid that you have here has to be equal to mu A liquid. Mu B solid has to be equal to mu B liquid. How is it possible? If we have a common intercept. Now for common intercept we require common tangent between these two curves. Now think of this white line, this white tangent line. This white line basically exactly does that. Right? It creates a common tangent. Now this is the common tangent. Now if you go to this intercept, you see basically mu A liquid equal to mu A solid and mu B liquid equals, and on this side it tells mu B liquid equal to mu B solid. Right? So you understood the common tangent is basically a graphical way of assessing the chemical equilibrium by solving these equations that mu A solid equals to mu A liquid and mu B solid equals to mu B liquid. If I solve these equations, what do I get? We get the compositions corresponding to E and F. Compositions corresponding to E and F. So basically, if I know the liquid solution model and the solid solution model, I can basically calculate the equilibrium. Right? We can basically calculate the equilibrium. So what we looked at or learned today is this common tangent construction. And finally, we have to remember, so this common tangent construction again, you should remember, note that common tangents did not pass through the minima, or did not basically pass through the minimum of the curves, right? So this is the minimum of the free energy curves. Free. So this is also called GX diagram, and this is called common tangent construction. And note that the common tangent did not pass the minimum of the free energy curves, right? Only if the minima are at the same level, exactly the same level, then you will have a horizontal common tangent, right? But otherwise, if you see here, you have alpha phase and beta phase that are in equilibrium. If you look at alpha phase and beta phase in equilibrium, and you want to use a common tangent construction, which I have done, this purple line basically gives you the common tangent. You see your the minima are here somewhere, but the common tangents are here, right? This indicates the composition of the alpha and beta phases in equilibrium, right? This is basically XB alpha equilibrium with beta. So XB alpha, this is basically XB alpha composition that is in equilibrium with beta, and this is XB beta equilibrium. So equilibrium, that when I'm looking at this equilibrium, we can tell alpha beta equilibrium, and it is beta alpha equilibrium, right? So basically what we are trying to say is that the equilibrium, the common tangent points, the common tangent where the common tangent touches these two curves, these 2 points basically correspond to the equilibrium compositions. These 2 points basically correspond to the idea that the solution of these 2 equations, like mu A alpha equals to mu A beta and mu B alpha equals to mu B beta. That is what is embodied. So that is what is embodied in the common tangent construction. So common tangent basically tells you a graphical way of estimating the equilibrium compositions. In fact, I have a Python notebook which I'll show. So basically, this is the common tangent. So this is graphical, common tangent construction. The basis is this equilibrium conditions. Okay, so note that I'll discuss further that we'll discuss another very important idea, So before that, I'll just quickly finish this lecture here with this, that liquid and solid, if they are regular solutions with unequal enthalpies of mixing, you often have a phase diagram where you basically have this liquid solid. So you can, this is something like you have two lenses here. So you have two lenses here, like this and then like this, and you basically can see here that this is like a liquid solid region, and then again there is a liquid solid region, and then there is one small point which is basically where it's turning, right? Which is where it's turning. In fact, the way it should be drawn is not this, but just think, draw it like, draw it like. Remember, this is a problem with the drawing here. With this act in general, this is much smoother. Okay, so basically, if you look at that, we can, yeah. So I'll come to this in the next lecture. And I'll explain to you that when you basically estimate liquid and solid to be regular solutions, you will see there is a definition from ideality, which I have discussed already, and you can look at how this common dynamic construction can be used to basically find the compositions of the phases that are in equilibrium, right? So that is something that you can see in the next